Let's move on to our next unit, that is stability of slopes. So slopes can be of two types, that is natural or man-made. Natural as in case of some hills and mountains, and man-made when we use the soil as the construction material such as earth dam, or in case of some embankment, then we use the soil on some slope. And when the soil is on the slope, so because a part of this gravity force will be driving this soil mass downwards, and because of that there are shear stresses in this soil mass. And if there are shear stresses, and if these shear stresses exceed the shear strength on any plane in this soil mass, then soil failure or the slope failure will happen. Now when we are doing this construction, so we need to be sure that the shear strength on any plane in the soil mass, it should be greater than the shear stresses. Now apart from the weight of the soil or the gravity force, the other forces that act to cause the instability in the soil are seepage. So if seepage flow is happening, because of that also the slope will be unstable. And apart from that, if earthquake forces are there or some vibrations are also there, so because of that slope will be unstable. So these are the forces that cause the instability. When we study this stability of slope, so we consider the limiting equilibrium. What does it mean? That we consider that shear stresses are just equal to shear strength on a given plane. Now let's define the factor of safety also here. So let's say to counter these shear stresses, a part of the shear resistance will be mobilized. So we call that as the mobilized shear resistance, which is a mobilized force to counter these shear stresses. And our maximum shear resistance will be, some maximum value will be there. So factor of safety we can define as maximum resistance divided by mobilized resistance. This is the general definition for factor of safety. We'll see it in detail, but for now let's just work with this. And after that, there are several assumptions which are involved in the study. That is, first is we consider only two-dimensional case. That is, we do not consider the width. And next is the C and phi, that is the shear strength parameter, they are constant for any possible slip surface. So their values are not changing. And apart from that, if there are seepage forces in the soil mass, so those seepage forces can be found out using flow net. These are the assumptions. Let's study first the infinite slope. So this is the infinite slope. So this slope part will be infinite and depth is finite. So this is a one element we have considered. It has width b and depth z. So if we want to find out the volume of this element considering unit width, so we can find this volume by dividing this into these three areas. So this is the triangle, this is the triangle, and this is rectangle. Here this width will be, if this angle is beta, so this is b cos beta, and similarly this is also b cos beta. And if this depth here is y, so this will be z minus y. And if you try to find out the area of all these three elements, that is two triangle and one rectangular, so this area is zb cos beta, which is also equal to the volume. And if we multiply it with the unit weight of the soil, that is gamma, so it becomes the weight of this strip, so that is acting downward. Now we have taken the components of these forces. So sigma z is working downwards or acting downwards. So this sigma z is nothing but the weight of the soil, that is gamma zb cos beta, because there is no other force. And this sigma n is the sigma n and tau are the components of this sigma z. So sigma n is the component perpendicular to this surface, and and tau is the parallel to the surface. So tau is nothing but the shear stress, and sigma n is the normal stress. So from this we can say that in this triangle this angle is beta. Sigma n is equal to sigma z cos beta, and tau is equal to sigma z sin beta. So sigma n is equal to gamma z b cos square beta, and tau is equal to gamma zb cos beta sin beta. Now if we consider the cohesionless soil, let's first see for the cohesionless soil. So we know that the shear strength is equal to sigma tan phi dash for effective stress. So this is the normal stress or effective normal stress. So here, because there is no seepage, so this total stress is equal to effective stress. So I can write the shear strength is equal to sigma n tan phi dash. And in the limiting equilibrium condition, shear stresses will be equal to shear stress equal to shear strength. From here, shear stress is this gamma zb cos beta sin beta. This gamma zb cos beta sin beta. And shear strength is equal to sigma n tan phi dash. Sigma n is equal to gamma zb cos square beta and tan phi dash. So this gamma zb will cancel out and cos beta will also cancel out. So from here we get that tan beta is equal to tan phi dash. Now for any slope which is having angle beta less than phi dash, it means that full or maximum angle of internal friction is not mobilized. So when beta is equal to phi dash, it means the maximum angle of internal friction has mobilized. Then for any value of beta which is less than phi dash, the maximum internal friction has not mobilized. So the max angle of friction that has mobilized, we call it as phi dash m. And factor of safety we can define from here as maximum resistance, that is tan phi dash divided by the mobilized resistance, that is tan phi dash m. So it is also equal to tan phi dash divided by tan beta. So from here we can say that for any angle of the slope which is less than the angle of internal friction of the soil mass, this slope will be safe, and for any angle that is beta greater than phi dash, it will fail. Now let's consider the seepage forces also. Seepage taking place. Well, this was our slope, this angle beta. This depth is z, and let's say water table is here. This depth here is h. So because of the seepage, effective stress will reduce. So sigma n now will be equal to gamma z minus gamma w h cos square beta, and shear stress will not change, that is gamma z cos beta sin beta. So why shear stress is not changing? Because water cannot take any shear stresses, so it is just remaining the same. So again, when shear strength is equal to shear stress, here we can write shear strength is, this is normal stress times tan phi dash, that is gamma z minus gamma w h cos square beta tan phi dash is equal to gamma z cos beta sin beta, that is the shear stress. Now I can also write that factor of safety is equal to shear strength upon shear stress. This strength upon stress, and so from here factor of safety is equal to gamma z minus gamma w h cos square beta tan phi dash divided by gamma z cos beta sin beta. Here this will cancel out and factor of safety here will be equal to 1 minus gamma w h by gamma z tan phi dash divided by tan beta. This is the equation for factor of safety when seepage is taking place up to some depth h, and from the that depth h is taken from the bottom, that you need to see because sometimes it will be given from the top also, so it is from the bottom. Now when h is equal to z, so the water table comes at the top, at that point factor of safety is equal to 1 minus gamma w upon gamma tan phi dash upon tan beta. This also we can write as gamma minus gamma w will be gamma dash, that is submerged unit weight, divided by gamma tan phi dash upon tan beta. So from here we can conclude that the factor of safety for a cohesionless soil on infinite slope does not depend on the depth. So it is remaining the same unless the seepage is taking place up to some other depth. It is not a function of depth. So if we want to plot the envelope or the strength envelope, that is sigma here, tau here. So for cohesionless soil, this strength envelope, that is sigma and tan phi dash, it will pass from here. This angle will be phi or phi dash, and the stress line we can denote something like this. This angle will be beta. So this point, this coordinate here will be representing gamma z cos beta sin beta. This will be representing gamma z cos square beta. So this part will be, this hypotenuse will be gamma z cos beta. So that was our weight or the stress that was coming. So that is the stress that is coming here. So we can say that if what this line shows here, it shows the stress at different points for different depths. So if we put the value of depth, other things are same in this gamma z cos beta. So beta is fixed, unit weight is fixed. So if we change the depth, so we'll get the locus of these points and this will be a line. So from here also we can say that when beta is less than phi, so this line will be below this strength envelope. When it is below the strength envelope, it means that it is safe. Whereas if beta is greater than phi, then it will fail for any depth. It is not a function of depth, because even if depth is here, so even then it is above this strength envelope, so it will fail. Whereas in case of C5 soil, we know that this is sigma here, tau here. We know that this strength envelope passes something like this. This angle here is phi dash, and stress will still be given as this line. So this angle here is beta, so the coordinates will be, this part is gamma z cos beta sin beta, that is shear stress, and this is normal stress, which is gamma z cos square beta. So here we can say that if depth coordinate is somewhere here, because at low depth this stress envelope is, or the stress line is below the strength line. This is strength and this is stress. So at some points which is having some value of depth, this line is staying below this strength line, but as we reach this point, at this point or at this depth, let's say it is the critical depth, at this depth what is happening here, the shear stress is equal to shear strength. So this is our critical case in this case, and we call it as the critical depth, denoted with HC. Now in this case we want to define the factor of safety. So factor of safety is again strength upon stress. The strength of the C5 soil is given as C dash plus sigma n tan phi. So sigma n is gamma z cos square beta, gamma z cos square beta tan phi dash, divided by shear stress is gamma z cos beta sin beta. So at critical depth what is happening, strength is equal to stress, it means that z is equal to hc and factor of safety is equal to 1. So from here we can write as gamma hc cos beta sin beta is equal to c dash plus gamma hc cos square beta tan phi dash, and hc here will be equal to c dash upon gamma cos beta sin beta minus gamma cos square beta tan phi dash. So hc we can write, if we take gamma common and cos square beta also common, that is tan beta minus tan phi dash cos square beta. Now look at this part, this is just consisting of angles. So this is a unitless quantity. So here I can write tan beta minus tan phi dash cos square beta is equal to c dash upon gamma hc, and this thing here we define it as the stability number, denoted with Sn. So Sn is equal to c dash upon gamma hc. So here we have got a stability number which is a dimensionless quantity, and it is involving three parameters, that is cohesion, unit weight and depth. So what does it do? We can prepare charts to check the stability using this stability number. That is the use of this. Now if we say that our actual depth h is less than hc, so that means the cohesion that is acting, it will be less than c dash. So let's say that is our mobilized cohesion which is less than c dash. So in that case the factor of safety with respect to cohesion we can write it as maximum cohesion divided by mobilized cohesion, and in terms of mobilized cohesion, factor of this stability number is equal to cm upon gamma h, or we can write it as Sn is equal to c dash upon factor of safety times gamma h. Let's say this is equation 1, and we also know that stability number is equal to c dash upon gamma hc, that is 2. So if we divide these two, so from here we can get that factor of safety is equal to hc upon h. So factor of safety with respect to cohesion is same as factor of safety with respect to the depth. but this is the factor of safety just for the cohesion. If we want to write the factor of safety in general, so the total factor of safety will be equal to maximum shear strength divided by, this is maximum divided by mobilized shear strength. So factor of safety we can write it as maximum is C dash plus sigma and tan phi dash divided by tau mobilized, and from here mobilized shear strength is equal to C dash plus sigma and tan phi dash divided by factor of safety. Now here C dash upon factor of safety we denote it with mobilized cohesion, and tan phi dash upon factor of safety is equal to mobilized angle of friction. So these are the different factor of safety involved in this, and so this also we can write as like this, tan phi m is equal to tan phi dash upon factor of safety. So this is also asked, instead of asking total factor of safety, you can be asked that what is the factor of safety with respect to cohesion, or what is the factor of safety with respect to angle of friction. So you can find it in this way. So this is it for the infinite slope. Next we will see the finite slope.